Reception on the dashboard here. Audio visual range 150 miles.
Ingenious, useful too.
What is it called?
In the future, it will be called the GPS.
Which is also known as the Global Positioning System. GPS was created by the Department of National Defense in the US and mainly attributed to Roger L. Easton. He came up with the idea after tracking the signals from the Sputnik satellite and realized that a distance could be determined. In 1964, he was awarded a patent. In 1967, the first navigational satellite was tested. In 1983, the Reagan administration allowed all civilians to use GPS, and in 1993, the satellite constellation was completed. GPS satellites are constantly emitting data. This includes the time the data is sent, where the GPS satellite is, and the orbit of other satellites. By comparing when the signal was sent to when it is received, the receiver knows how long the signal traveled to reach it. The receiver also knows that the signal travels at the speed of light. Using the distance equals velocity times time formula, it can calculate its distance from the satellite. Since the data also includes the location of the satellite, the receiver knows all the possible positions it could be in. This is represented by a circle with the center being the satellite location and the radius being the distance. If the receiver finds a second signal, it can narrow down its position to 2 points. If the receiver finds a third signal, it can triangulate its position at the only intersection between the three circles. Of course, this is only a 2D representation. The process is similar in 3D. Instead of circles, the possible locations exist as spheres. A fourth satellite is needed, however, for error correction and finding altitude. Because the GPS signals are 1575.42 MHz, they only travel through line of sight. There must be at least 4 visible satellites at all times for the receiver to work. Currently, there are between 4 to 10 satellites visible at any given point on Earth. GPSs are prone to 4 specific types of errors. Signal multipath error occurs when GPS signals bounce off of buildings before reaching the receivers. This increases the distance and the time it takes for the signal to reach it, therefore disrupting the calculation. Ionosphere and troposphere delays occur when the signal hits the different parts of the atmosphere, which causes it to travel at different speeds. This is because the speed of the signal is affected by the charged particles in the ionosphere and the gaseous particles in the troposphere. The military uses 2 different radio frequencies to compensate for this error. Receiver clock errors occur when their clocks are not synchronized with the satellites. Unlike the satellites, receivers only use quartz clocks, which are much less accurate when compared to atomic clocks. And finally, orbital error occurs when there's a discrepancy between the position of a satellite and its reported position. The GPS constellation needs at least 24 satellites to work, but the US maintains 31 satellites for redundancy. Each satellite orbits at an altitude of 20,200 kilometers. Like we learned in physics class, these satellites are in constant freefall towards the Earth. We can find the acceleration of the satellite at that altitude using the formula gravity is equal to the gravitational constant times the mass of the Earth divided by the distance between the center of the Earth and the center of the satellite squared. At that altitude, the satellite accelerates towards the Earth at a rate of 0.56 meters per second. Using this next equation, we can calculate the velocity of the satellite as it orbits around the Earth. After plugging the velocity into the period formula, we find that it takes approximately 11.9 hours for the satellite to make one orbit around the Earth. We can also calculate the relative time of the satellite according to Einstein's theory of relativity using this formula. In this equation, t0 is our time, so we'll just sub in 1. V is the velocity of the satellite, so we'll get that from the page before. And c is the speed of light. In the end, we get t to be equal to 1.0000000000834. So for every second that occurs on the satellite, this amount of seconds will occur here on Earth. Even these minute differences matter, especially over time, which is why GPSs account for it, to preserve accuracy. There are many positive effects to the GPS. They help guide airplanes, boats, and ground vehicles. They even can prevent military action, like when a commercial airliner accidentally flew into Russian territory and was shot down. This was actually the event that prompted President Reagan to allow all civilians to use GPS. It allows parents to track their kids or their pets. It helps search and rescue teams find people in distress faster. It allows researchers to track and study migration patterns. It helps scientists predict earthquakes. It helps helicopters map forest fires, and it helps us get to where we need to go. The pros of GPS are endless. There are some cons though. It can be used to create deadly self-guiding weapons for mass destruction. It can be used by stalkers to track their victims, and studies have shown that the use of a GPS can actually reduce the function of the hippocampus in the brain. This is the part that is responsible for memory and navigation. Although the entire development costs of the GPS are unknown, Congress set aside $965 million last year for the GPS program. All of this money comes directly from American taxpayers. In the last 16 years, the US have launched 12 new Type 2F Boeing satellites. These satellites are meant to keep the current system, Navstar, operational. In 2020, the US are launching the next generation satellites called Type 3A. These satellites will be able to provide accuracies to the size of a forearm.